Hello, good morning, everyone, and welcome to this seminar today. We had some technical problems. Momento. Okay, now, as I said, we had some technical problems with the YouTube and the link to the seminar, but now we are ready to start the seminar by Alessandro Patti. Just remind you that during the seminar or at the end of the seminar, you can ask the questions you have or the doubts, and at the end of the seminar, Alessandro will answer them. So before starting the seminar, just a few words to introduce Alessandro. Alessandro, thank you for accepting our invitation to give this seminar today. He was awarded his PhD by the Rovira y Virgili University in 2007, working on molecular simulation of self-assembling block copolymers for the synthesis of mesoporous silicates. After that, he went for a postdoc at Utrecht University, where he was for 3 years. And there he was working in the nucleation and growth of colloidal crystals and the dynamics in colloidal liquid crystals. Then in 2010, he was awarded the Beatriu de Pinós postdoctoral fellowship by the Catalan government, and also Juan de la Cierva postdoctoral fellowship by the Spanish Ministry of Science. And then he was working at the Institute of Advanced Chemistry in Catalonia on self-assembly of block copolymers. Then in 2014, he moved to the Department of Chemical Engineering at the University of Manchester as lecturer, and he was promoted to senior lecturer in 2018. And in April, he will join the Department of Applied Physics at the University of Granada as Marie Zambrano Senior Research Fellow. His work or his interests are related to molecular modeling and simulation, with specific expertise in Monte Carlo and molecular dynamic simulation of soft matter systems, especially on phase behavior, dynamics, and microrheology of colloidal liquid crystals and polymer nanocomposites. At the moment, he is supervising 1 postdoctoral researcher and 3 PhD students, and he has successfully supervised the PhD thesis of other 3 students and 1 postdoctoral fellow in the last 4 years. And today he's going to speak about equilibrium, self-assembly, and out of equilibrium dynamics of nanoboards. So, Alessandro, thank you again. Welcome. And
thank you very much, Esther, for this very nice introduction. And thank you very much also to Jose Miguel for arranging this seminar, and clearly to Eva Gonzalez Noya and Enrique Lomba for inviting me today. I need to apologize for not being in person in Madrid at the Rocasolano Institute. That was my actually original intention, but due to the fact that our university is warmly suggesting us to avoid unnecessary or not extremely necessary trips, and considering the situation we are living now, I thought it was much better to have this seminar online. But it will be my pleasure to be in Madrid and visiting the Rocasolano Institute as soon as this will be possible. So, as you said, Esther, thank you for your introduction. This work is about the phase behavior and the dynamics of nanoboards. And this particle is very interesting because they can self-assemble in a wide spectrum of mesophases. And we will discover what mesophases are especially interesting throughout this talk. You are also very kind, Esther, in giving a picture of the systems and the research interest we have in my group in Manchester. And this is actually a quite brief explanation of this presentation of this system. So we definitely are working in my group in Manchester on the phase behavior and dynamics, and also more recently on microbiology of colloidal systems, especially colloids of anisotropic particles that are able to form liquid crystal phases. We also work on polymer nanocomposites, which are systems made by a polymer matrix incorporating nanoparticles. We have studied the phase behavior, we have studied the dynamics, and also the rheological property of this system. And we study how incorporating nanoparticles can actually improve mechanical, thermal, or rheological properties of the pristine polymer. We also studied in the group the self-assembly of amphiphilic molecules or blockopolymers, for instance, or surfactants for the synthesis of lyotropic lipid crystals of micellar system. And in collaboration with Alessandro from the Pablo de Olavide University in Seville, we have over the last year developed a stochastic molecular simulation technique to study the dynamics of colloids. So we will talk a bit about dynamic Monte Carlo along the talk. So I would like to acknowledge, first of all, the people who played a crucial role in the development of this work and in achieving the goals, the scientific goals of this work. So I already mentioned my friend and colleague Alessandro. Matthew Dennison was a former PhD student in Manchester, and during these years of collaboration, he was postdoctoral fellow at the Technical University in Berlin. And then my colleague, Professor Andrew Masters from the Department of Chemical Engineering in Manchester, and the people from my group, Efran, who graduated last December, now is a doctor, he finished PhD in December, Luca, who is a PhD student too, and should be finished by the end of this year. And Daniel Corbett was a former postdoctoral researcher in my group. So they are basically the people who made this work possible. I prepared a few slides just to make everyone familiar with what system we are going to talk about during the presentation. I wasn't sure whether everyone is familiar with colloids, so I prepared just a few slides to summarize what colloids are, why they are relevant, and why they are relevant for this specific research topic. So colloids are two-phase systems. We have a dispersed phase that could be solid, could be a gas, could be a liquid, so they could be solid particles, they could be bubbles or droplets, and they are dispersed in a liquid, in a fluid, in a dispersing medium. The size of these particles or the dispersed phase should be between a few nanometers and a few microns, which is the usual size of nanoparticles. The reason why this is important is that these particles, droplets or bubbles, are expected to be dispersed in this medium. They should not sediment, they should not settle out. If they were larger, they would be heavier, and most likely they would sediment. There are different possible combinations with respect to the physical state of the dispersed phase and the dispersing medium. This is a table taken from Wikipedia, where we see that the dispersed phase can be a gas, can be a liquid, can be a solid, and also the dispersing medium can be a gas, can be a liquid, it can be a solid. So there are many possible combinations. Possibly the only one that is under scrutiny is a gas in a gas, simply because gases are mixable between each other. This is the cell that is our reference here. So the system that we are going to focus on in this talk are solid particles dispersed in a liquid. This specific system are referred to as colloidal salts or colloidal suspension. colloidal particles diffusing in a medium, in a solvent like water, show a very peculiar dynamics that is usually referred to as Brownian motion. The term comes from the Scottish botanist Robert Brown, who in 1927 studied the diffusion of small pollen particles in water. The impact of this study was realized only almost 80 years later, thanks to the theory developed by Einstein, Smoluchowski, and then especially the experiment of Perrin, that of course led to the unambiguous discovery of the molecules. The motion that you see here that seems to be quite random is due to the collision between the colloidal particle itself and the solvent molecules around that here are modeled as very small black dots. Of course, when Robert Brown for the first time observed these movements, was not sure what was this due to, but the impact of this first experiment was completely and fully recognized at the beginning of last century. The energy associated to these movements are relatively low if we measure with let's say our daily experience, right? They are in the order of few kT per particle, where Kb is the Boltzmann constant and T is the absolute temperature. So at ambient temperature, this energy, this thermal energy, are of the order of 10 to the minus 21 joules. So for us, are very almost insignificant amount of energy. You need only 1 joule to raise an apple by 1 meter. So 10 to the minus 21 joules are very small amount of energy. Nevertheless, they are large enough to completely change the phase behavior and the dynamics of colloidal systems. Now, why are colloids important? Well, first of all, they can be used to better understand what occurs at the atomic and molecular scale. So they are used very often as model systems to understand what happens at atomic and molecular scale. This is why there is a lot of interest in decorating these colloidal particles with patches that can simulate bonds between molecules and can give the option to actually generate superstructure or supercluster that can better mimic specific molecules and the way these molecules interact to each other and bond to each other to form crystals. There are processes that are too fast at the atomic or molecular level to be detected by conventional microscopy. Nucleation and growth is one of them. So what people do is to understand these processes through the colloidal scale. Even though they are excellent model systems, colloids have an importance by themselves. We can use colloids, for instance, to synthesize porous solids. We can use colloids to build, to design and manufacture nanostructures that have specific optical properties, for instance. Photonic crystals is a very good example, and they are used for controlling the propagation of light. So colloids, this message is colloids are very important as model system. Colloids are very important in material science by themselves. If the particles that we use to investigate colloids are anisotropic, so they are not spherical, then they have the ability to form liquid crystals. Liquid crystals are state of matter in between liquids and crystals. They are fluids, so they flow like a liquid. The only difference is that if in simple liquids molecules don't show any specific ordering, in liquid crystals, so in these fluids, molecules or particles are oriented. And in some cases, they can also be positionally ordered. So in this frame here, you see that rod-like particles are oriented along a common direction that we call a nematic director, and form what is usually called nematic phase. So this is a nematic liquid crystal phase. It's a fluid where particles are oriented along a common direction. If they are also positionally ordered, so they form some layers that are quite well defined, then they form, we call this symmetric liquid crystals. So there is still a degree of orientational ordering, and on top of that, we also have a positional ordering. Now, if rather than looking at rod-like particles, which are uniaxial particles, we investigate more complex shapes like boards or nanoboards, which are biaxial particles, the realm of liquid crystals that can be observed is much richer. Why? Well, because these boards can be oriented along the main axis only, so they form uniaxial nematic liquid crystals, but we can also see that the minor axis can be oriented too. And if that occurs, we have ordering along 3 directions, and these are called biaxial nematic liquid crystals. Now, the optical properties of these 2 phases are rather different. And what motivated our research at the beginning was to understand whether what are the response times that would be associated to switching from this configuration here to this configuration here. So moving from a uniaxial nematic phase to a biaxial nematic phase by switching on an external field. And of course, investigating what is the dynamics of reorientation of the biaxial nematic phase to the uniaxial nematic phase when the external field is switched off. Now, this was the ultimate research goal that we had when, at the very beginning, when we started to study this specific system. However, this task was very far in time. Why? Because there were a 2 sets of challenges associated to this research. One was mostly related to the phase behavior, and the other one to the dynamics. So, challenge 1, the question that we had first to tackle was, do biaxial nematics really exist? What are the conditions that we need to apply to stabilize this system? Can monodispersed system of cuboids, of nanoboards, stabilize biaxial nematics? If not, do we need a degree of size dispersity? And if we are interested in applying an external field, how strong this field should be to promote the switching from uniaxial to biaxial without destroying ordering? That was the first set of challenges, and this is what we will specially talk today. The second set of challenge, which is for those of you who do simulation, is possibly already clear. Mimicking the dynamics of cuboids is not trivial, because to the best of our knowledge, we don't have soft potential that could describe this particular shape. We can look at alternatives, one of them being the use of an array of spherical Lennard-Jones particles. But as again, those of you who do simulation know that the computational effort of describing a single interaction site as a single cube would be with hundreds of interaction sites is very relevant. This was done in the past to study phase behavior, but we didn't want to follow this path. Our intention was to apply our own dynamic Monte Carlo simulation technique that allows one to study the dynamics of hardcore objects, of hardcore particles, and still quantitatively reproduce the Brownian motion of them, their Brownian motion. I will also towards the end of the talk, say something about the dynamics of this object, but we will first start with this first set of challenge. So why do I call challenge? Well, because over the last 50 years, there was a quite long list of theories, and I'm reporting here only the most relevant ones, that confirmed or suggested the existence of biaxial nematic phases. But they made quite strong assumptions, of course, to make the theory more accessible, more manageable. One assumption was the neglecting the presence of positionally ordered phases. So no nematics, no crystal phases above the nematic phase. Another assumption was to limit the orientation of particles to 6 orthogonal possible directions, which is usually referred to as Wonsing model. Other works assume that particles were perfectly aligned, so their main axis could not move, but only rotation around it were acceptable. The consequence of this was a number of phase diagrams where the biaxial nematic phase, as you can see here, resulted to be especially stable. These are phase diagrams where one of the relevant parameters is, of course, the geometry of particles. And all these studies agreed on the fact that for some specific geometry, it was possible for the system to phase transform directly from an isotropic phase to a biaxial phase. This specific geometry is called self-dual shape, and is exactly in between a disc-like and a rod-like geometries. So in between an oblate and a prolate geometry. Now, I especially like this work by Taylor and Herzfeld from the 90s, because the same authors first show a phase diagram of how the region of stability of biaxial nematic would be if they neglected the symmetric and columnar and crystal phases. And then they show another phase diagram where the biaxial nematic phase, the region where this phase is stable, shrinks significantly when positionally ordered phases are included. And the same author mentioned that it is even unclear whether this tiny region would still be stable if they also allow the particles to rotate freely. This theory, as I said before, restrict the orientation of particles to only 6 orthogonal orientation. So it makes use of this Wonsing model. From the other side, by contrast, what do experiments suggest? Now, we need to wait a bit longer to see an unambiguous evidence of the existence of the biaxial nematic phase. This is a PRL published in 2009 by the group of Frege in Utrecht. They used goethite particles, which are biaxial particles, and observed the existence of biaxial nematics. These are 2 capillars at different global density. What makes this interesting is that their system was not monodispersed. The particles were polydispersed, significantly polydispersed in the 3 directions, in length, width, and thickness. Now, and even though they call them board-like, they are definitely biaxial, but they are very irregular. That means they are not monodispersed in size and not in shape. We need to wait 10 years, even 10 years more, and we get to 2018 to see a very nice synthesis of regular cuboidal particles, monodispersed and very regular cuboidal particles in the group of Zihong Nie at the University of Maryland. They synthesized these particles made of ammonium sulfate and covered by tetraethylorthosilicate. So they synthesized this particle and characterized their phase behavior. This is a phase diagram where they report the reduced length and the reduced weight of particles. And the dashed line you see here refer to different values of this parameter. This is an anisotropy parameter, theta. When theta is 0, which is around here, particles are self-dual shaped, so they are not prolate, they are not oblate, they're exactly in between. For theta larger than 1, then particles are prolate, this rod-like. And if theta is lower than 0, then, so it's negative, then particles are disc-like or oblate. Now, they see here a wide spectrum. They study a wide spectrum of anisotropies. They observe the presence of nematic phases, the presence of nematic, uniaxial nematic phases and columnar phases, but there is no evidence of the existence of biaxial nematics. I stress, these are monodispersed systems, while the system that we observed before in this PRL are significantly polydispersed. So these are the first questions that we ask ourselves. Can monodispersed cuboids form biaxial nematics? Experiments suggest that this is not necessarily the case, but theories from the last 50 years would indicate that that is actually the case. So if not, shall we introduce an element of size dispersity to stabilize the biaxial nematics? And what about the rotational degrees of freedom? So to answer this question, we, a few years ago in 2017, we started to analyze, we tried to answer these questions by running molecular simulations. And our system was quite relatively simple. We used hard nanoboards of different width and constant thickness and length. So the width ranges from T to L, where T is our unit length. So we basically map the phase behavior of rod-like and disc-like particles, including, of course, the self-dual shape. We run Monte Carlo simulation in the NPT ensemble. Temperature here doesn't play any role because particles are hardcore. And so we monitor the packing fraction, or if you want, the volume fraction, to check equilibration of the systems. What we did was to expand the pre-assembled crystal phases and also compressing isotropic phases to better locate, with more accuracy the phase transition between different phases. And we evaluated also the order parameters by the by diagonalization of this tensor here, where lambda I refer to the orientation of particles in space. Diagonalization of this tensor give us eigenvectors, which correspond to the nematic the direction of orientation of particles, and the eigenvalues are the uniaxial order parameter. We can, of course, also calculate the biaxial order parameters similarly. And depending on the numerical values of these order parameters, we might have an isotropic phase if both of sets have a very low value. We have uniaxial phase if the uniaxial order parameter is very large and the biaxial is very low, or if both of them are quite large, then we have a biaxial phase. The threshold value of the biaxial parameter that suggests the presence of biaxial nematics was set to 0.35, which means this parameter here should be at least 0.35 for one to observe biaxial nematics. That was arbitrary and set according to the observations that we made across all the system that we studied. Lower values of this biaxial order parameter between 0.2 and 0.35 suggested the presence of, let's say, a very weak biaxiality with a residual oblate or prolate uniaxial ordering. So this is basically the classification that we use to characterize our systems. Now, the order parameters give us an understanding of the orientational ordering of the phase, but we also need a positional, an insight into the positional ordering of the phase to completely characterize the system. So we calculate per correlation function in the direction of the nematic director and in the direction perpendicular to the nematic director. And these are very important because they allow us to distinguish between nematic phases and semantic phase. So in the top frame, you see this per correlation function, which measure basically the mutual distance between particles in the direction of particle length for prolate particles. You see the typical profile observed when you have a layered structure in the semantic phase, and then the typical flat profile that you see when there is not any positional ordering, which is expected in nematic phase. Similarly, we did the same for oblate particles. In this case, the reference direction is the one along the particle thickness rather than the one along the particle length, but the meaning is exactly the same. Periodic peaks observed in semantic phases and the almost flat profile observed for nematic phases. So with all this information, we could build our phase diagram that you see here. This is a volume fraction or packing fraction versus reduced particle width. So you see there's a very rich phase behavior with nematic phases, prolate nematic and oblate nematic phase, different semantic phases, including the presence of a biaxial semantic phase, columnar phases, crystal phases, but we could not observe the biaxial nematic phase, even at the self-dual shape, which is approximately here, where theory suggests that biaxial nematics are especially favored to fall. We asked then Matthew and Andrew, our theoreticians, to help us with theoretical analysis, just to have a confirmation of what we observe with simulations. And they obtained a calculated phase diagram of cuboids using a non-Sager-like theory to study the isotropic to nematic transition that they modified to allow particles to reorient freely in the three directions. And they confirmed basically our result. They confirmed the first order character of the isotropic to nematic transition. And to study the formation of semantic or columnar phase, they used a different approach. They used bifurcation analysis. So they basically calculated where the nematic prolate or nematic oblate phase were metastable with respect to semantic or columnar phases. In this case, they assumed that particles were perfectly aligned along their main axis. That assumption was completely fine because we calculate the order parameters in the nematic phase, and we observe that this has a very large value, very close to 0.9. So assuming that particles were perfectly aligned and was completely fine. So we also asked them to try to locate where the transition from uniaxial to biaxial nematic phase would eventually occur. What they did was, again, to assume particles to be completely aligned and allow only the minor axis to reorient, so to shift from uniaxial ordering to biaxial ordering. And what they observed was that the biaxial phase, the uniaxial phase, became metastable with respect to the biaxial phase only at very large packing fractions, where the presence of nematic phase is already preempted by sematics or columnar phases. So the conclusion was, for theory and for simulation of monodisperse system, was not possible to see the formation of biaxial nematic phase. Now, we need also to mention that in 2018, the group of Marla and Dijkstra in Utrecht calculated the phase diagram of the same particles that we studied, but up to anisotropies that were very large. So you see here, this is the ratio, the reduced length, the ratio between length and thickness. This is the area that we studied in our work. And Professor Dijkstra and her group studied up to 34, L star equal 34. So extreme anisotropies, extreme lengths, as they also mentioned in their paper. And it seems they were able to find the biaxial nematic phase here. Now, if you remember what I showed you a few slides back, this experiment by Nie and co-workers also studied the same anisotropies, but they were not able to see the formation of biaxial nematics. The main difference here with respect to simulation is that these are experiments in capillaries. So they are stuck in phase diagram, while the phase diagram that we see here is a bulk phase diagram. So that might make a difference. In any case, as far as I know, there are no experimental evidence today of the existence of biaxial nematics for such long particles. So we're still waiting for that. So assuming that for normal anisotropies and monodispersed system is not possible to see biaxial nematics, we thought, okay, let's see if in adding a level, a degree of size dispersity, things would change. And why that? Well, that came from the paper published in 2009 in the group of Frege. They observed that size dispersity was key to obtain biaxial nematics. And this vision was actually supported by a later theory, again, based on the Swansea model, that established the existence of biaxial nematics in binary mixtures and in polydispersed systems. These four frames here, these four phase diagrams, packing fraction versus molar fraction of the long species, refer to a different geometry of the short and long particles. While here we have a polydispersed system where I think we took around 20 different geometries, 20 different species. So it's not a real polydispersed system, but this is theory, and it is not straightforward to have a continuous spectrum of geometry. So we limit this analysis to 20. It is interesting here that for binary mixtures and polydispersed system, the phase diagrams show a very ample region where the biaxial nematics is stable. But there is not a direct transition from isotropic phase to the biaxial nematic phase. This tetracritical point here, where four different phases are at equilibrium, connect the isotropic phase to the biaxial nematic phase through the uniaxial nematic. This is also true in the binary mixture here. Okay, so the only limitation here in this theory was the use of the Swansea model. So by simulation, we allow the particles to orient freely as they went and check for the existence of biaxial nematics. We use the same geometries that have been used in this phase diagram here, exactly the same, with the only difference that we allowed particles to reorient as they wished. And this is the phase diagram that we obtained. This is a reduced pressure versus a volume fraction of the long particle species. At sufficiently large pressure, the system phase separates into an isotropic phase rich in short particles and the nematic phase rich in long particles. If we increase pressure even further, then the system splits into different nematic phases. So the conclusion was, again, that no evidence of biaxial nematics was observed. Then we were left with the only chance, the only opportunity, last opportunity was, okay, let's look at size dispersity, not just a binary mixture, but the full size dispersity, where we can mimic the polydispersity by using Gaussian distribution of sizes, with some assumption to speed up simulation. The particle thickness was the same for all of them. The particle width was the square root of the length, so all particles are self-dual shape. And the polydispersity changed between 0.05 and 0.3. So you see here how the minimum value of the maximum value of the particle length change. So we can approach very, very polydispersed systems. So by doing that, we could actually observe the biaxial nematic phase. And this is the phase diagram that we obtain. So the system needs, these systems need a rather significant size dispersity. Here it's the minimum value is 0.18 to form a biaxial nematic phase. And as you can see here, there is no evidence that from the isotropic phase, we could directly get to the biaxial nematic phase without passing through the uniaxial nematic phase. So there is not a direct transition from isotropic to biaxial nematics, in agreement actually with a long list of work, simulation work that studied similar biaxial particles or different biaxial particles. So we are not alone in this conclusion, which breaks with previous theory, but is in agreement with the works where the orientational degrees of freedom were actually included. So the first main conclusion is, yes, we can use polydispersity to stabilize biaxial nematics. But what if we want to use monodispersed system and an external field? Can we still get biaxial nematics? And the answer was yes, we can. We studied the transformation from an isotropic or a uniaxial nematic phase by applying this simple external field. So this is not an electric field, this is not a magnetic field, it's just a very simple field that we couple to one particle axis, specifically to particle width, and with a given intensity. We study then the phase diagrams, and we see that at some specific field intensity, biaxial nematics phase can form. If the field is not, the intensity of field is not specific, is not especially large, then we still see the occurrence of weak biaxial phases. What is interesting to see is that for the self-dual shape, the transition to the biaxial nematic requires the least energy. So if we were interested to see, to select a specific geometry that would be more energetically sustainable, then we would choose the self-dual shape because it's the one that requires less energy to transform an isotropic phase or a uniaxial phase into a biaxial nematic phase. So of course, these open new questions related to the kinetics itself of this transformation from the uniaxial to the biaxial nematic phase that finally took us close to answer the question that was originally the motivation of this work. What is the dynamics of phase transformation when we apply an external field? So what is the response time to reorient a uniaxial phase into a biaxial phase? What happened when we switch this field off? And how does the particle geometry influence the response time? We answered this question by applying the dynamic Monte Carlo methodology, and I will not go through the details here. The only piece of information I'd like to make clear is that dynamic Monte Carlo is very similar in the essence to a standard Monte Carlo technique. The only difference is that we need to set the maximum displacement, the maximum rotation, according to the ability of particles to diffuse in a medium of a given viscosity. And this is quantified by the diffusion coefficient, the translational and rotational diffusion coefficient that depend on the geometry of the particle. If we do that, we can recover through the acceptance rate in Monte Carlo simulation, we can recover the unique Brownian dynamic time step. So those of you who are interested to know the details of this simulation technique, there is here a list of papers that we published over the last 10 years for monodispersed system, polydispersed system, and other system or processes. So we applied dynamic Monte Carlo to study the reorientation of uniaxial to biaxial and back upon application of an external field, which is the same as the one that we used to study the phase behavior. So what do we see here? Well, we see that if we map over time, the uniaxial order parameter and biaxial order parameter, we see some changes that allow us to quantify the response time of this switching. So the uniaxial order parameter, as you see here, this is this black line corresponds to the uniaxial order parameter, is constantly the same. Why? Because in the uniaxial nematic phase, this parameter is already quite large, and it will not be affected by the reorientation of the minor axis. However, the biaxial order parameter is initially very low until we switch the field on, and then it achieves a given value and stay constant. It stays constant up to the time when we switch the field off, and then goes back to 0. So we define this response time or switching time as the time that the system takes to take the biaxial order parameter up to 95% of its steady state value. We do this for the field on and the field off response time. We do this for, this specific graph refers to a specific geometry. We did this for all geometry that we studied and obtained this curve. One refers, so the orange curve refers to the switching on, so when the response time when we switch the field on, and the green one refers to the response time when the field is switched off. As expected, the orange curve, so the switching on takes less than the switch off because we are applying an external field. We are forcing the system to reorient. While when the field is switched off, we let the particles freely achieve the new steady state. What is interesting to see is that prolate particles are relatively faster than oblate particles. So rod-like particles are faster, reorient much faster than disk-like particles. But there is also another interesting difference in the kinetics of their orientation. This is usually called self-Banov correlation function, and is usually calculated for displacements. We use it to calculate angular displacement, so reorientation. And we did this to calculate, it's basically the probability of distribution of angular displacements over time, how fast or how slow particles are in reorienting. So frame A refers to switching on, and frame B to switching off. And each curve refers to a different geometry and to the same period, instant of time, which is 35 for this frame and 100 for this frame. So you see here that if we look at prolate particle, orange curve here, in that period of time, they can rotate more than oblate particles, black line here. So their rotation is more significant. But they do this in a more heterogeneously. So the distribution of rotational displacement or angular displacement is quite broad. The peak is approximately 1.5, but then we have a very long tail, which means there are particles that are quite fast in reorienting, and particles that are quite slow in reorienting. Oblate particles are, on average, slower. They reorient slow, but when they do that, they do this homogeneously, which is quite interesting. So depending on what we have in mind in terms of application, we might need a fast reorientation, and we are not very much interested in whether or not the particles are doing that homogeneously, or we might need particles to reorient homogeneously. It doesn't matter if they take longer. So conclusion, I hope I show you that system of nanoboards are very interesting because they have a very rich phase behavior, because they were studied over 50 years or more. And finally, it seems that we could unambiguously find the evidence of the existence of biaxial nematics in monodisperse systems, thanks to the application of an external field, and in polydisperse systems. We also show how we could, by applying an external field, we can switch from a uniaxial nematic to a biaxial nematics, and what conditions are there to control these kinetics if we want a fast reorientation, if we want a slower reorientation, and the geometry also set the amount of energy that we need to provide for this transformation to occur. What are we going to do next? And then I'll stop here. So I think you all know that most of liquid crystal applications make use of molecular liquid crystals rather than colloidal liquid crystals. So what we have learned at the colloidal scale is what we want to use as a guide now to understand whether the biaxial nematic liquid crystals can be observed at the molecular scale. How are we going to do that? Well, we will start from specific biaxial molecules. We will use coarse-grained models that are not as simple as the ones that you use in this talk, but a bit more elaborated. And we will study the phase behavior and switching dynamics. What are we already doing, or what else are we doing with nanoboards? We have studied, this is a work with Alessandro in Seville. We have studied the phase behavior and dynamics of nanoboards and nanocubes under confinement, so in cylindrical nanopores. And we look at the dynamics as compared to the bulk dynamics. And what we are doing now with my student, Luca Tonti, is to study with real electric field, not with an external field that is like a toy field. We study the formation of chains in system of nanocubes or nanoboards that would change the rheological property of this fluid. This fluid are usually referred to as electrorheological fluids. And they are very, very important in a number of applications where a change of viscosity, an abrupt change of viscosity is needed. Braking systems in vehicles is one of them. So I think I'm just left with acknowledging the sponsors that have funded this research. And of course, I would like to thank all of you for your kind attention. Thank you very much.
Thank you, Alessandro, for the presentation. I think it was very interesting and also very nice that you did this introduction at the beginning, because not all of us are involved with this kind of materials, or we don't know much about it. So now we have time for questions. Just see if anyone has any question in the chat in YouTube. We have a short delay between your presentation and YouTube, but maybe I will ask. No, there is one question. Let me read it. Eva Gonzalez Noya, thank you. Thank you for a very interesting talk. Can you provide an intuitive explanation as why polydispersity is needed to stabilize the biaxial nematic phase?
Yeah, thank you, Eva, for your question. Yes, we believe that the reason why polydispersity is key is because it contributes significantly to the destabilization of the nematic phase. So when you have particles that are very short and very long, it becomes very difficult to observe nematic layers. Because for a layer to be observed, you need a sort of a periodic spacing between them. And this periodic spacing, this sort of characteristic spacing, characteristic length is provided as long as you have a good degree of monodispersity. But as soon as particles becomes too different from each other, you can see here that at especially large polydispersity, there is a very significant difference in particle length, then keeping these layers stable becomes more and more difficult. So we believe that these contribute to stabilize the nematic phase with respect to the semantic phase, which, sorry, the diagram was here. Oops. Here, we believe that the reason is there. We can destabilize the semantic phase, and as a result, we see the occurrence of the biaxial nematic phase.
Okay. Let's see if we have more questions. I will ask you something. It's not. It's more curiosity regarding. I mean, you saw some photographs of this kind of particles made basically in inorganic materials or salts. Is this possible then, or what is the difficult part, as you know more about the literature on the topic, to do this in metals or in polymers, for instance, because the 2 or 3 examples that you saw are salts or hydroxides, or I don't know how difficult this then.
So this is not my area of expertise.
I
so
know,
I don't
that's
know
why
what,
I say that it's curious, but maybe you have information from literature. Or,
what the limits would be to synthesize cuboids using different materials. That I really don't know. What I can tell you is that it took a very long time to get to the shape that you can see here, that are really impressive. And they used, as you said, they use salts, and the technique they used is very specific, so it's beyond what I actually can comment on. But to stabilize these particles, as you can see here, and to make them, so to tune their interactions, what they used then was this tetraethyl orthosilicate. So the particles are made by this ammonium sulfate, but then covered by a tetraethyl orthosilicate, which they can tune the mutual interactions between them. Now, what other options will be there, even by using a polymer? This goes beyond what I can actually tell you.
But it seems that they are all crystals. So they have order inside the particle, and then that's why you can have these nice structures that then you can.
Yes, definitely. Yes. At the atomic scale, there is order inside the particles, definitely. And possibly this is the main driving force for particles to appear so regular. But the details of the synthesis of these particles, I'm sorry, I'm not prepared there.
No, it's okay. It's just curiosity. More questions? It seems we don't have more questions. Yes. Jose Miguel Manceño, I'm curious about changes in the macroscopic properties, optical, magnetic, electrical, of the different phases of materials suffering the transitions you have mentioned. Do you know some examples?
Okay, so we are actually studying something on how the macroscopic properties change. We are doing that now. We have just started. We are using microrheology to study the viscoelastic response of liquid crystals, different liquid crystals. We started with rods, but we are now doing this work with Luca, with nanoboards and nanocubes. And microrheology is a technique that allows you to infer the viscoelastic response of the host phase by introducing a small tracer. So what one does is following the dynamics, the diffusion of a small tracer to infer the viscoelastic response of the host material. And what we have observed in nematic phase and semantic phases is that it is very interesting there actually, and this is something that we haven't sent to publication yet, we are working on that, is that we can study the elastic and viscous moduli in the relevant direction. So in the direction of the nematic director, in the direction perpendicular to the nematic director. And this is very interesting to see that the response are different. The response of the elastic and viscous moduli in this specific direction are quite different. And the resulting microviscosity, which is the viscosity experienced by the probe particle, which is not exactly as the bulk viscosity, is affected by the long-range ordering. So the theories that have been so far used to study isotropic fluid cannot, and that of course take into account the density of the system, cannot be directly used to study the rheology, the viscoelastic response of systems with a degree of ordering. Because what we are seeing now is that the liquid crystals, that of course have a degree of ordering, cannot, their viscoelastic behavior cannot simply describe neglecting this ordering, this long-range ordering. This is what we are observing now. So the first result about rheological properties tends to indicate that directionality is very important. And this is something we are actually working on right now. More generally, in which something we are not working, but in terms of optical properties, if Jose Miguel is more interested in this aspect, when we have a uniaxial phase and when we have biaxial phase, we move from one optical axis to two independent optical axes. And how can this optical axis be used? Well, if you want to send a piece of information, light, well, you can use a single optical axis and you can transfer a single piece of information. But if you have two independent optical axes, you can split this piece of information in two independent pieces of information and transmit these two pieces of information according to different time scales, according to different, the content of the same information will be different. We are not working on that, but it's a possible application of our interest of switching from uniaxial to a biaxial phase.
Okay. There are no more. Thank you very much, Jose Miguel.
No problem. Thank you, Jose Miguel.
So then we can finish our session today, and we thank you again very much for this presentation. So we hope that next time you can come and give the seminar here.
Yeah, that would be great. Thank you very much, Esther, okay, and thank you very much to everyone.
Thank
you. Bye.